Okay, hello and back. Okay, a couple more examples, and then we're done. All right, so this is going to be example 3.5. Let me make sure we're focused here. There we go. Example 3.5, which I'm inserting in between example 3 and 4 for the book. Okay. Think about this situation here. Water is filling a rain barrel at a rate of R equals F of T, right? So there's a function that function R equals F of T that expresses the rate at which, the amount of water in the barrel is increasing. Okay, where T is in hours. Write a definite integral that expresses the amount of water accumulated in the barrel in 24 hours, starting from time 0 when the water starts accumulating. Okay, so anyway, so let's make a graph to kind of illustrate this. Here we go. Okay, so this is going to be T, and this is going to be R, which is F of T, right? And then there's some kind of a function. R is a function of T, right? And it's, I don't know, something like that. We don't know if the rainfall is constant, right? But we know that, the amount that overall, the amount, unless water is leaking out of the barrel, it's not, the amount of water is decreasing, right? I mean, water is not flying back up into the sky, right? And so this is going to be, so the R is never going to be negative. So, so that's not going to, so that's going to be an upward slope like that somehow. Okay, so let's say that's 24 hours right there from 0, and then, oh, look, that's the interval we want, and what we've got to know is that the accumulation, the total amount of water in the barrel, let's call it capital R, right, of T, that is the area under this curve for a given value of T is what R of T would be, right? And we know that R primed is equal to little r, which is F, right? F of T, yeah? Okay, anyway, so remember that the accumulation of water in the barrel, the amount of water in the barrel, very roughly, is going to be the length times the width. It's going to be the x units times the y units. Well, the x units are hours, and the y units are going to be, so the x units are hours, right? And the y units, those are, as it said, that's liters per hour, right? So that when you multiply, that's going to be liters, right? So here, so the definite integral, you understand, is multiplying time, very roughly speaking, time, x times y. So the x is, or the y is f of t, and the x is dt from 0 to 24. And if we had some, and that's as much as we can do with that problem there, right? If we had an equation for f of t or some data, then we might be able to actually calculate that. Okay, so that's example 3.5, and you're going to see something like that on your homework. Okay, so then here's a bigger example, one that I really like. Okay, it says here, as you can see, now this is, I'm going to zoom in so we can see it better, but this is on page 260 in your book. It's a really fine example of how science uses math, even areas like, that wouldn't seem very mathy, okay, if you're maybe just studying them in school. But look at this situation. Biological activity in water is reflected in the rate at which carbon dioxide, CO2, is added or removed. Plants take CO2 out of the water during the day for photosynthesis and put CO2 into the water at night. Okay? Animals put CO2 into the water all the time. as they breathe. Okay, this graph here shows the rate of change of CO2 level, the CO2 level in a pond. Okay? So this over here is not the amount of CO2. This is the speed with which CO2 level, that CO2 is increasing or decreasing at a given time, the speed at which it's increasing or decreasing. So this is another speed function. Okay, at dawn, there are 2.6 millimoles of CO2 per liter of water, or really we don't need to, that's just how you would measure it. The amount of CO2 is just going to be in terms of millimoles here. And so this rate over here, since this is the rate of change, it's going to be, as it says here, millimoles per hour is the rate of change. So this is, again, the speed or the velocity graph, and then this is going to be the time over there, right? Okay, so what we're trying to calculate here, what we're getting at, okay, so let's see what the question is. At what time was CO2 level the lowest and what was the highest? We want to estimate how much CO2 enters the pond during the night from t equals 12 to t equals 24. Estimate the CO2 level at dusk, 12 hours after dawn, and does the CO2 level appear to be approximately in equilibrium? Well, okay, so let's make sure we understand this graph here. This graph is from dawn, starts at dawn. So this is sun up. So this is, sun up right here. And then this is sundown, dusk. So noon is in between here, 6 hours after dawn, approximately. Then this is the daytime here. This is the daytime part of the graph, up to 12. Then here, this is dusk throughout the night. This would be midnight. And then 24, another 12 hours later, this would be dawn the following day, is what that would be. So this is the nighttime part of the graph. So that's why they want us to work. That's why they say nighttime is from 12 to 24. Okay? So you can see here that according to this graph, since this is a speed graph, it says here that the rate of change, the speed, was negative. Well, remember, negative, that makes sense because during the night, the CO2 level is decreasing, right? So the rate of change should be negative, so this speed here is negative. Here, during the day, CO2 is accumulating again, right? In the water is accumulating again. And so here, so the rate of change of the CO2 is positive, okay? Right here at dusk, the rate of change is 0. Okay, so where was CO2? Okay, so the level of CO2 is the amount. So the amount of CO2, remember, is going to be the area under the curve, right? For any given amount of time. So this is the area under the curve. So this represents, all this represents the amount up to a certain point. So this is the amount of CO2 up to, say, noon, right? That would be the total amount of CO2 accumulated, or rather, up to noon, right? Anyway, so you can see here that around here, okay, so here it's lowest, it's accumulated at its lowest amount by dusk, whereas you notice it's starting to accumulate more, and it adds up and up and up and up. Keep in mind that it's the rate of decreases, the rate of changes, or the rate of increase is decreasing, but you can see that the amount of CO2 is still increasing because the area is going up, right? So here, lowest is down here, highest is up here because the area is lowest over here and the area is highest up there. Okay, does that make sense? Okay. Okay, so we want to calculate the total change in CO2 in the pond from from dusk to dawn of the following day. Now that's the total amount of CO2 accumulated, the total amount that was added in over that period, right? So using the fundamental theorem of calculus, we calculate it like this. If we keep in mind that little f That's the rate of change. That's the speed here. That's the rate of change, that's CO2 per hour, right? We want capital F, which is the total amount of CO2, right? Keep in mind, for all of these graphs, this curve that we're finding the area above, that's always going to be the rate of change of the area under the curve. So that means here, as they put it, f prime of t is equal to little f of t, right? You take the rate of change of this, and that's that. Or you take the antiderivative of this, and that's that. Or as we're about to do here, you take the area under the curve here, and that gives you the same thing as taking the antiderivative, right? So here's how they put it, okay? We're going to have the area under the curve at 24, so we're going to take the antiderivative and evaluate it at 24, minus the antiderivative evaluated at 12, and the difference between them is, well, that is the total area under the curve, which is this area here that we want, right? So how do we do that? Well, okay, so it's a natural phenomenon, and you notice that it's, we've got general trends here, but there's no smooth function that would predict that behavior exactly, right? So we don't have an equation for f of t. So guess what we're going to do? We're going to do a Riemann sum, right? We use the values f of t from the graph to construct a left Riemann sum approximating this integral with 6 intervals, and with each one a delta t of 2. So where are those 6 intervals? Well, they're over here, right? We want to get this area from 12 to 2, so here are the 6 intervals, just like this, right? And it says we want to have a left sum, and that's the first integral. So that's the first interval. So we're going to do, since we're doing the left sum, we'll do this rectangle here, this rectangle, this rectangle, this rectangle, this rectangle, right? Because see, we're making each of our 1, 2, 3, 4, 5, forgot that one, 6 rectangles. We're anchoring them on the left boundary of each interval. So all we have to do here is we look up on the graph, we look up what, so the area, we look up what the heights of the rectangles will be on the left. So we're going to use whatever f of 12 is times delta 2, because notice that the delta t here is 2 hours. Then f of 14 times 2. Then f of 16 times 2. Then f of 18 times 2. F of 20, all the way up to f of 22, which is this one here. Now we find the height of all of those rectangles and multiply each one by 2 to get that area. Now we can either read that from the graph, or in the next page they actually give you the heights. So here is f of 12, which is 0. Here's f of 14, which is 0.45. Here's f of 16, which is 0.35, and so on, f of 22, which is 0.12. And you see here, oh look, those are the same heights that we're using here for the rectangle, and it all adds up to 0.278, right? So we used a Riemann sum using the left sum method that we've done in quite a number of our different problems before that, okay? So here, okay, so the rate of change, so thus between 12 and 2 is a CO2, we would say the change in CO2 level from 12 up to 24, given by this definite integral here, is about 0.278 millimoles. Now that's millimoles per liter. Oopsie, you can't see it, sorry. Oopsie. I'll do that again. Okay, so up here between t equals 12 and t equals 24, the change in the CO2 level, right, the amount of CO2 that was added in was f of 24 minus f of 12. We added in 0.278 millimoles. Now, don't worry about the millimoles per liter. That's just a way of measuring the total amount of millimoles, okay? So really millimoles are the units here, okay? So that's how that goes. All right, to find the CO2 level at T equals 12, so C, we use the fundamental theorem to estimate the rate of change during the day. We do F, same thing, F of 12 minus F of 0, right? And that would be from here to here, right? We want this area here would be 0 to 12, okay? Well, using the same rectangle procedure that we just did, we would get negative 2.3, negative 0.328. You're going, wait, how can it be negative? The reason why it's negative is that sorry, lost my thing for a minute. The reason why it's negative is this is area under the curve, right? So actually what we're about to do is not, and this is a tricky bit here, because this, you understand, is the x-axis. So we're going to measure this area down here, okay? So using the same process, we measure that area to be negative 0.328, right? And the beginning amount was 2.6, so we just subtract that. And so the amount under the curve is 2.272. Okay? So that's how that goes. Okay, so anyway, so D. Okay, that was the equilibrium question. Does the CO2 level appear to be in equilibrium? And the answer is more or less. I've kind of driven it over here, but you're going to see this area, which is the area under the curve, not this, you understand. This is the area under the curve. That's the negative area that we just measured, right? Okay, that's in terms of the actual, what does that mean in terms of the lake? That's the amount of CO2 that was removed from the water. So this is the amount that was added to the water. This is the amount that was removed from the water, right? And by the way, just so we're clear, I wasn't looking very clearly here, but when we're drawing the rectangles, we're not actually including those. Here's the x-axis, and we're measuring, we're measuring from 0 up. So this area is positive. This is the amount that's added, right? And that's the amount that over here that we measured on our table here, in which we added up to get the 0.278, right? And then you can see here that, so that represents CO2 added. This area under the curve that we represents area taken out, subtracted from the water. And we'd still use rectangles to do it, you understand. Okay, like that. Okay, and we'd add up those rectangles the same way. Okay, and so since it's negative, that means, yeah, CO2 taken away. All right, and so last question, D. What you're meant to notice is that those two areas are about the same, roughly speaking. So the amount taken away from the water during the night is the amount that's added to the water during the day, which indicates a healthy ecological balance there, at least as far as CO2 goes. Okay, very good. All right, so I'm going to post the homework, and this will get you a start on the homework. Okay, and if you've got any questions about this, especially maybe about what we just did here or about how to use the calculator, just send me an email, okay? And if you want, I can write up directions, written directions for the calculator. If you need them, just let me know by email, okay? Bye.